Hello everybody. Today I'd like to talk to you guys a little bit about the Labflow Boyle's Lab experiment. So in this experiment we're going to have a setup of our system that is essentially going to be a syringe that looks a little something like this. We're going to have a closed end to the syringe, and it's going to have a certain volume that is associated with it. In addition, we're going to have a syringe volume that we're actually going to read off. So the entire volume that we're going to be dealing with is going to be the volume of the tip plus the volume of the syringe. The syringe has a plunger in it. This plunger has an area at the top here that is going to be important when we're trying to calculate our pressures later. For the first measurement, we're going to have everything pretty much set up just like this, all by itself. And the total pressure inside of the syringe is going to be equal to the atmospheric pressure outside of the syringe. There will be no masses added, and therefore there's no forces on the syringe. Now, for measurements 2 through 6, we're going to have a system where we flip the syringe upside down, and we started to add masses to the top. Now the force of those masses is going to be pushing down on the plunger and compressing the gases inside of the syringe. In this scenario, the total pressure inside of the syringe is going to be greater than the pressure of the atmosphere on the outside. As the amount of mass goes up, the forces on the plunger are going to go up. The volume is going to be smaller as the plunger pushes the air down, and the pressure is going to rise. For measurements 7 through 11, we're going to have the opposite situation here. We're going to flip the syringe so that the closed end is on top and the plunger is on the bottom. We're going to add weights to this plunger that are going to pull it down. And as it pulls down, it's going to increase the volume in here, and it's going to reduce our pressure. So again, as the masses go up, the forces go up. This time the volume is going to go up and the pressure is going to go down. The total pressure inside is going to be less than the pressure of the atmosphere. So, starting with what we know, we are going to be given an atmospheric pressure. This is going to be given to us in units of inches of mercury. We can multiply by the correct conversion factor and get this in a convenient unit of pascals. We also have the volume of the tip, this V tip, and that's going to always be equal for us to 1 milliliter. Next, we're going to have the area of the plunger head. This we saw before is going to be pi r squared for the plunger head. We could measure it in various different ways, but they just gave us a value to work with of 1.77 times 10 to the negative 4 meters squared. Meters squared being already a convenient unit for us, we don't have to convert there. Similarly, for each and every one of the measurements, there's going to be a mass added that's going to be in kilograms. Kilograms is our preferred unit, so we don't have to do anything there. And we're going to have the volume of the syringe in units of milliliters. Okay, moving on to what we're going to need to calculate for table 2. The first thing you're asked for is the total volume of the syringe. This is going to equal the volume of the syringe plus that additional tip volume. This is going to be a constant for us of 1, so it's just going to be the volume you were given for the syringe plus 1 in each case. The next thing that they're going to ask for is what is the force on the plunger. We're going to have units of kilograms times meters divided by seconds squared. This is going to be proportional to the mass that we've added times a constant that is the acceleration due to gravity. Our masses were already given to us in kilograms, so what we need is to have this acceleration in units of mass per second squared, and that value will always be the same. It is 9.8 meters per second squared, at least near the Earth's surface. The next value they're going to ask us for is what they're calling P syringe. I actually don't really like that name very much because it's not the pressure inside of the syringe, but instead what this is the amount of pressure that was either added by this force to the atmospheric pressure or taken away from the atmospheric pressure, depending on how we have our plunger set up. So this is a difference in pressure due to the action of the piston on the syringe. Regardless, it is going to be the force that we just calculated divided by the area of the plunger head. Our area, again, will always be a constant for us, so we're going to take this force value and divide it by 1.77 times 10 to the negative 4 meters squared. Now, due to our different setups that we have for measurements 2 through 6, we're going to have our pressure total is going to be greater than the pressure of the atmosphere. And what we're going to do is take the syringe pressure we just calculated and we're going to add it to the pressure of the atmosphere to get our total pressure inside of the syringe. Do not forget that we have calculated this with units of pascals. This was originally given to you in inches of mercury, so you're going to need to convert that to pascals in order to get your total pressure also in units of pascals. For measurements 7 through 11, our total pressure is going to be less than the atmospheric. And you can see what we're going to do is we're going to take that atmospheric pressure in pascals and we're going to subtract the pressure of the syringe we calculated for those measurements. The final column that they're going to want you guys to calculate is going to be the pressure times the volume. This is going to be equal to PT, the total pressure, times the total volume that we calculated initially up here. If we think about this for a second, this PV value is going to be equal to roughly nRT. Since the temperature of the room did not change and we can assume that the syringe was in thermal equilibrium with it, this value here becomes a constant. The number of moles didn't change either since we started off with a certain volume that we trapped inside the syringe. So our PV values should be pretty close to one another. And the only real variation we're going to see in them is going to be due to the inaccuracies in our measurements. And the next section, we're going to look a little deeper into that error.